Okay, in this video we're going to work backward from exponential differentiation. So let's work forward from exponential differentiation just as a refresher because it's been a while. So if I give you a problem like this and I'm going to ask you to differentiate, I would like you to pause this and actually try it just to see if you can remember how to find the derivative of something that looks like this. So pause this, go give it a try, and then come back. Okay, welcome back. I hope you actually did it. So to find the derivative, if you'll recall, for an exponential function, if I had something like a to the u, then the derivative is a to the u times the natural log of a times u prime. So in our case, we have dy dx is equal to 3 to the power of x squared, so don't change that initial function, multiplied by the natural log of a, so that's the natural log of 3, and then multiplied by the derivative of the exponent, so that's 2x. Okay, that was a good reminder. Now I want to show you how important these three parts are, because these three parts were the derivative of this original function. So when it comes time to work this backwards, I'm going to have to think about where we began in order to, I should probably put parentheses around that because that looks funny. We need to think about all of these parts in order to work backward. So let's just take a look. So if I ask you to integrate something like this, and I'm just going to start with where we ended off. I'm going to rewrite it so that it's like this instead. So I'm going to write this as 2x natural log 3 to the x squared dx. So what gives me a hint, what gives me a clue that this was an exponential, of course, is this part right here. This part is the a to the u part. So that's here. That's this a to the u. That's part of the derivative. The other part of the derivative is this part right here. The natural log of 3, that's the natural log of a. And the natural log of a is part of the derivative. I'm not sure why I'm duplicating it up there, but that's okay. And then finally, since u was equal to x squared, du is 2x dx. So that means that this 2x and this dx were the u prime, or du, if you will. So what I know then is if I make all of these replacements, so we know that u is x squared, we know that a is 3 in this case. If I rewrite this, the natural log of 3 is the natural log of a. I have a to the x squared. And I have 2x dx, which was u prime. That was the derivative of the exponent. I should have put this as a to the u, because that's what I'm trying to do here. So I made this full-on u substitution that got me back to the derivative of an exponential function. So the antiderivative of those three things, in other words, what was the function that gave us this as the derivative, is a to the u plus some constant. Well, in our case, a is 3, and u is x squared. So because I had all three parts, those three parts were really important, I was able to find the antiderivative because it had all of the key ingredients for the derivative of an exponential. Let's try another one. There was a lot going on there. Let's try a second one. Let's see if we've got 6 ln 2 and then times 2 to the power of 4x dx. Okay, I can see this is an exponential, so I'm looking for all three of those parts. First things first, I know that a is going to be 2 because that is the base of this exponential. So a is going to be 2 in this case. U is the exponent, and u is 4x, so du is 4 dx. I see that I've got a 6 here, So there's a couple ways I can go about this. I think what a lot of you are doing is not trying to make that 6 work. Instead, what you're saying is, well, I know that 1/4 du will be dx, and that's going to make it a lot easier to make a replacement here. So let's take a look. We have 6, which is just a constant. I can pull that out in front of the integral as well. I have the ln of a. I have a to the u, so ln of a, here's a to the u, and then this becomes, dx becomes 1/4 u prime, or 1/4 du. If I combine those constants, so if I multiply 6 times 1/4, I get 6/4, or 3/2. So if it helps you to move the 3/2 out so you can see everything, now we have the 3 parts that we need. The antiderivative of ln a to the u times du, or u prime, is just a to the u. In other words, these were the 3 parts that gave us, that was the derivative of an exponential. So we end up with 3/2 times a to the u plus c, and in our case, a it was 2, u was 4x, and plus a constant. Okay, I'm going to give you one to try on your own. And then we'll do something just a little bit harder, and then that's pretty much it. So give this a shot. Let's see, I've got 3x 4 to the power of 6x squared dx. Oops, I forgot one part, didn't I? ln 4 dx. Okay, give that a shot. Think about a, think about u, rewrite this, use substitution, and then find the antiderivative. Okay, welcome back. I see that a is going to be 4, and u is 6x squared. Du then is 12x dx, and if I take 1/4 of that, I'll get 3x dx. Okay, I'm going to make my substitutions. 3x dx becomes 1/4 du. I'm going to write that at the end. I have the ln of 4, so that's the ln of a. And I have a to the u. Okay, the antiderivative of that then is 1/4 a to the u plus some constant. And we know that a is 4 to the 6x squared plus some constant. No, you cannot, unfortunately, you cannot multiply 1/4 times 4 and make it 1, because this is 1/4 to the first, and that's 1/4 to the 6x squared. They cannot be multiplied together. This is as far as you can go. Or you can write it like this, whatever you prefer. Okay, let's do one more. And this was what I was going to do last time, but I figure we should do this together. I'm going to redo that same exact problem, but without the ln of 4. Okay, let's take a look. We've got a equals 4. We've got u equal to 6x squared, du is 12x dx, and 1/4 du is 3x dx. We have a problem though. Our problem is we're missing something. We're missing the ln of 4. So let's rewrite what we've got for right now. We have the 3x dx becomes the du, and this becomes a to the u. So I have the a to the u, I have the u prime, I'm missing ln a. Well, the nice part about the natural log of a is that it is a constant. So what I'm going to do is not mess this thing up, but I need an ln of a in here in order to make this antiderivative work. So I'm going to use a fancy form of 1, because I know that if I multiply by the natural log of a over the natural log of a, that really is just a form of 1, and I'm not changing the integrand at all. Okay, the part that I need is the ln of a that's on the top. So I'm going to rewrite this just a little bit so you can see what I'm talking about. If I rewrite that, ln a over ln a. I'm going to write it as the natural log of a times 1 over the natural log of a. I forgot my 1/4 on the du. You should have said something. I forgot that 1/4. Okay, what I've got now is all of the parts that I need. I have this 1/4 that I'm going to pull out here. I have a 1 over ln a that's a little bit extra as well. I have a to the u. I have ln a. I have du. These two are just constants. The natural log of a is just a constant. So what I can do is move both of those outside of the integral. And now I've got all of the parts I need. I have all 3 parts. The antiderivative of this is just a to the u. So this becomes a to the u over 4 times the natural log of a plus a constant. If I replace everything, I've got 4 to the 6x squared over 4 times the natural log of 4 plus a constant. Okay, that's pretty much it. It's kind of all of the same process, rinse and repeat. So go give it a try and see how you do.